Today I'm going to talk about this fully dynamic earthquake cycle simulation with fault damage zones. And this is in collaboration with Prithvi Thakur, my previous graduate student, Yihe Kaniko, who is now a faculty in Kyoto, and also Peng Zhai, who is a new student in my group this year. And I think Ahmad and Esteban have already given great introductions about the near fault damage. So let me just start from like a brief introduction about the seismic observations first. So we know that this damage tends to accumulate with the fault displacement. And around the major mature faults, we can observe these well-established fault zone structures from the seismic observations. So here, this table just summarizes the material properties of major fault zones. You can see that these stress-free fault zones are usually 100 to 400 meters wide, with 30 to 60% of loss reductions for both P and S waves. So this will be the parameter space we are using in our cycle simulations. But I also want to note here that from the geodetic observations, these stress-free fault zones can be wider in the order of kilometer scale. And on the right, I just want to demonstrate a beautiful example about the fault zone guided waves, which are what people use to observe these fault zones in the beginning. So you can see these fault zone guided waves are the dispersive high frequency wave trends that can follow behind the P and S waves. And you can use the frequency content amplitude of these waves to constrain the spatial extent and also the velocity contrast of this layered medium. We have also done some synthetic analysis to understand the wave phases inside this low velocity structure based on elastic approximation. So here we just put a point source inside this fault damage zone, like a low velocity structure, and record the stress perturbations on the fault. So you can see that within a short distance, there are PP, SP plus PS, and also SS reflections. And if you wait for a longer distance, you can also see these different kinds of head waves that can propagate along the interface of the fault damage zone and also can propagate faster than the direct waves inside the fault zone medium. So this means that all these different kinds of wave reverberations can actually cause both positive and negative stress perturbations that interact with the rupture dynamics. So the question will be how these different kinds of dynamic waves can change the earthquake cycle behaviors. So here we are using a spectral element method to simulate a mode 3 rupture and aseismic creep on a two-dimensional stress-free fault embedded in an elastic medium. So essentially, this is like a simplified veil of an earthquake on a San Andreas fault. And we also re-implemented the algorithm developed by Kaniko et al. In 2011 using the Julia language and also the algebraic multi-grade scheme. So now we have a CPU speed up of about 50 times compared to the previous MATLAB version. And here in this conceptual figure, we're just demonstrating the different kinds of fault zones that we are going to test in our simulations. We focus on 3 different kinds of fault zone geometry. So here, the first one is just a tabular structure that extends through the whole seismogenic zone. And then the third model here is a shallow fault zone that ends at a certain depth, like 6 to 10 or 12 kilometers in our simulations. And for the last model here, this is mimicking a flower structure using a trapezoid geometry. So here we have more distributed damage close to the surface, but more concentrated damage deeper in the fault. I also want to demonstrate our frictional parameters and stresses here just to help us understand what is the width of the seismogenic zone in our simulations. So if you look at the A minus P parameter shown by the green line here, you can see that our velocity weakening region is from 2 kilometer to 13 kilometer in the simulations I'm going to show next, which means that the velocity weakening region is about 11 kilometer. So I'm going to use this to calculate the W over H star ratio later as well. It is easier for earthquakes to nucleate inside the fault damage zones because we have this reduction of the nucleation size. And here we need to make sure that we can resolve this nucleation size in our cycle simulations. And this equation here is from the Rubin and Imperial equation, which is more applicable for like A over B ratio larger than 0.5. So here you can see that H star is directly proportional to the shear modulus of the near fault materials. Canico et al., they also did a revision of the equation based on a layered medium. So here the H star layer is the theoretical nucleation size for earthquakes inside this tabular structure. And you can see that this is related to the thickness of the layer and also the rigidity contrast between the layer and the host rock. So just to demonstrate how this low velocity structure can affect the nucleation size, here we're plotting the nucleation size for L equal to 8 millimeter, and also the same stress conditions I showed in the earlier slide. So if you look at the top figure here for a shear wave velocity of 100%, this is like a homogeneous medium. So for a homogeneous medium, the theoretical nucleation size is 3.9 kilometer. And then as the shear wave velocity inside the fault zone decreases, we can see that once it decreases to about 60% of the host rock, which is pretty typical for the mature stress-free fault zones, the nucleation size will be reduced by 20%. And then if you look at the bottom figure, you can also see that as the damage zone gets wider, it can actually have a more pronounced effect on the nucleation size. So as the fault zone changes from 150 meter to like about a kilometer, the theoretical nucleation size will be reduced by about 40%. And for the simulations I'm showing today, we are going to focus on those narrow fault zones first. So for those narrow fault zones, the theoretical nucleation size is about 3 kilometer, which means that the W over H star ratio is about 3.5 for these simulations. And for this W over H star ratio, we are going to observe like mostly periodic occurrence of large earthquakes. So besides the nucleation size, we also want to make sure that the cohesive zone size is well resolved as well. So here in the simulations, we have tested different resolutions, and we find that a JRL node spacing of 20 meter can ensure that we have 5 JRL nodes inside the cohesive zone. Although the resolutions here are important, we find that they don't really affect the onset time of the earthquakes that much. So if you look at the left figure here, this is the peak sleep rate for one earthquake in our simulation for different resolutions. And you can see the onset time of these earthquakes actually agree with each other pretty well. However, we find the node spacing or the resolution can affect the dynamic part more. So for example, here we tried 3 different node spacing, 40 meter, 20 meter, and 10 meter. These are the sleep rate functions at 7 kilometer for 2 different earthquakes. So you can see that especially for this particular earthquake, when we use a 40 meter node spacing, we see a lot of oscillations in the sleep rate functions. But then if we reduce this to 20 meter and 10 meter, we are seeing like these artificial oscillations are muted, but we still have some oscillations following behind the major sleep pulses. So these are actually corresponding to the wave reverberations from the fault zone boundary and also from the free surface. So this is the first point I want to make here, is that these dynamic waves can actually result in source complexity that is not observed in our homogeneous simulations. So here we are just showing the sleep rate distribution for the deep fault damage zone simulations and also for the 2D flower simulations. These are just the representative earthquakes within like several hundred years of earthquake cycles. So you can see that after this rupture front propagating to the shallower part of the fault, there are a lot of oscillations following behind, like these oscillations and these. So these are actually the reflections from the fault zone boundary and also from the free surface. We can also draw a cross section from like 7 kilometer depth here and plot the sleep rate functions again. So the fault zone sleep rate functions are shown by the blue color and homogeneous is orange color. So you can see that after this major sleep pulse, there are some reverberations or some extra sleep pulses due to the wave reflections for both the default zone and 2D flower structure. But for the homogeneous medium, we're only seeing this one extra pulse, which is related to the free surface reflection. Well, because of these different kinds of dynamic waves, we are generating some small scale stress heterogeneities, and these result in earthquakes with different sizes and hypocenter locations as well. So here we are plotting the co-seismic sleep and interseismic sleep for deep fault zone simulations and also shallow fault zone simulations. And the red stars here show the hypocenter locations. So you can see that for the deep fault zone simulations, we have these small earthquakes followed by bigger earthquakes, and also the alternating locations of shallow and deeper hypocenters. And when we truncate the damage zone width at 10 kilometers here on the right, we can also see that the hypocenter locations are shifted to the shallower part as well. And all the earthquake hypocenters are actually inside this fault damage zone structure. So this is indeed what we saw if we compile all the simulations that will have fault zones and at a certain depth. So here, this is the histogram about the hypocenter locations for fault zones that end at 6 kilometer, 8 kilometer, 10 kilometer, and 12 kilometer. When the fault damage zone is 6 kilometer, we see that most of these hypocenters are still below the damage zone. So this is because the fault is loaded from below and the hypocenters are still close to the boundary where we have this transition from the velocity weakening to velocity strengthening friction. However, once the damage zone gets a little bit deeper, we are seeing that a lot of these hypocenters are inside the damage zone or close to the material boundary. And for a little bit like deeper fault zones, like 10 kilometer and 12 kilometer, we are also seeing clustering of seismicity at both shallower and deeper part of the fault. So this is also like the so-called bimodal distribution of the seismicity as observed in some regions in California. And even for deep fault zones with similar W/H star ratios or RU numbers, we can also observe this variability in hypocenter locations. And this is mostly because we sometimes have this propagation of the slow sleep events into the velocity weakening region. So here we're just showing some preliminary results for fault zones with different width, but similar W/H star ratios. And you can see that for these two different simulations, there could be slow sleep events propagating into the velocity weakening region. And as a result, the hypocenters are shifted to the shallow part of the fault. So we are seeing this shallow and deeper hypocenter alterations in our simulations. If you're interested in this topic, there is a recent study by Shuai et al. In Sichuan University who investigated the hypocenter variations in fault damage zones using a much wider parameter space. So they have tested this using A/B in the range of 0.1 to 0.8, and also RU in the range of 10 to 100. And they showed that this kind of variation of the hypocenters tends to happen more often when A/B is larger than 0.5 and RU is less than 20. And here is their AGU presentation, which is S51B05. So here I show that in this kind of fault zone simulations, the slow sleep events can actually propagate to the velocity weakening region. And another effect I want to show today is that as we allow this near fault materials to change over time, we can actually see these kind of slow sleep events more often. So the first one here is this co-seismic damage and interseismic healing. we know that after these big earthquakes, there could be reductions in the seismic wave velocities. So for example, this is a recent observation from Ridgecrest. You can see after the magnitude 7.1 earthquake, there was like about 6 to 7% P wave reduction close to the fault. But then this P wave also increases pretty quickly over time within like 2 weeks time scale, but it didn't really go back to the pre-earthquake level. And if you look at the map image here, you can also see that most of the damage here actually occurred close to the fault. And here is another observation from the Landers earthquake source region from like years of active seismic surveys. So they showed that there could be a slow healing of the near source velocities over a 5-year scale. So this is a much longer healing time compared to the healing time for the Ridgecrest source region. And here we are trying to simulate this cold seismic damage and interseismic healing under an elastic approximation. So we allow this shear modulus of the near fault structure or the fault diameter zone to be reduced by several percent after the earthquake. And then the shear modulus can increase over time during the post-seismic and interseismic period. For some simulations, we also have this permanent shear modulus reduction. So this corresponds to the permanent damage after the earthquake. And when we have this permanent damage, we can actually see that there could be an evolution of the fault zone structure, which features first like relatively large shear modulus and then to like relatively low shear modulus. So this is like a transition from the immature fault state to the mature fault state. And we actually see very contrasting behaviors in the sleep rate history and also sleep distribution between the immature fault state and the mature fault state. So for this immature fault state, the shear modulus inside the fault zone varies between 85% and 80%. So the blue lines here show the maximum sleep rate on the fault, and you can see that when it is higher than the dashed line, which is 1 millimeter per second, this is considered to be an earthquake. And we actually see very irregular recurrence intervals between the earthquakes in the immature fault zones. But once we get to the mature fault zones, which has a shear modulus between 45% and 40%, we are seeing a very regular earthquake cycle, like the earthquakes here occur every 50 years or so. We can also see a difference in the rupture patterns and cold seismic sleep distribution between the immature and the mature fault zones. So for the immature fault zones, most of these earthquakes are actually subsurface, and sometimes they can be very small as well. And between these earthquakes, we're also seeing the slow sleep events again propagating into the velocity weakening region. But then once the shear modulus is reduced to like more than 45%, we can see that the earthquakes start propagating as sleep houses, and also they become this surface rupturing event that occur every 50 years or so. So we try to understand what is actually contributing to the slow sleep propagation in our simulations. And we find that if we don't have this cold seismic damage and interseismic healing, for the frictional parameters we're using here, we don't really have any slow sleep events inside the velocity weakening patch. So for example, here, we just keep the shear modulus inside the fault diameter zone to be 65%. And you can see that we only have this periodic occurrence of large earthquakes. But then if we still start from 65%, but then like this to be reduced by 5% after the earthquake and heals back, we start seeing a lot more slow sleep events developed close to the previously ruptured regions. So because these slow sleep events can release the stresses on the fault, so they kind of limit the size of the subsequent earthquakes. And also as a result, we're also seeing this alternating hypocentral locations. Another interesting phenomenon is that when we have these slow sleep events, for example, highlighted in the orange circles here, they could also delay the occurrence of the subsequent earthquakes and make the recurrence intervals longer. So this is one type of the temporal change of the near fault materials. And another type that I'm going to show today is what we call the precursory velocity change. So this means that before the earthquakes, sometimes people can observe that there are temporal variations of the near fault seismic wave velocities. And this has been a popular topic back to like 50 years ago. And recently there have been more observations in the laboratory experiment and also in field observations. So for example, here, this is a fast stick slip experiment. And the red lines here show the P wave velocities close to the fault. You can see that before this fast stick slip experiment, which is represented by the reduction of the shear stress, there is about 1% P wave velocity reduction within like 0.5 seconds. And this kind of precursory velocity change has also been observed, for example, in the SciFold project. So this is like also a precursory velocity change observed within like half a day before a 2005 magnitude 3 earthquake. And here we know that when we have this precursory velocity change, this can introduce an extra shear modulus reduction that further reduces the nucleus size. However, this effect won't be a linear effect because how much this nucleus size is reduced also depends on the precursory onset duration. So here, to understand this effect, we are going to prescribe a precursory velocity reduction as the fault starts accelerating. And then after the earthquake occurs, like once the unfold acceleration is 0 and the steep rate is below the seismic threshold, which is 1 millimeter per second, we also allow this velocity to heal back to the pre-earthquake level. So it doesn't really affect the second earthquake in the cycle. So here, just to give you some more details about the numerical part of this simulation, the timing of the precursory velocity change is solely determined by the steep rate threshold when the fault starts accelerating. So for example, here, we actually prescribe a precursory velocity change of 0.5% once the maximum sleep rate is 10 to minus 8 meters per second. And after that, the earthquake occurs 20 days after the precursory onset. So the precursory onset duration here is 20 days. And we also find that the same sleep rate threshold can actually give very different precursory onset time. So we present here 2 different kinds of simulations based on L equal to 2 millimeter and L equal to 8 millimeter. So when L is relatively small, a 10 to minus 8 meter per second sleep rate threshold can actually give 20-day precursor. But when L is equal to 8 millimeter, for example, shown by this point here, a 10 to minus 8 meter per second actually gives a 1-day precursor. And also once this sleep rate threshold increases, we also see that there should be a reduction of the precursory onset duration as well, although the relationship will be again different for different frictional parameters. So to better understand these simulations, we also measure the nucleus size by using the fault patch that has sleep rate higher than 1 millimeter per second, which is our seismic threshold at the start of the earthquakes. So then we normalize this nucleus size by the theoretical nucleus size for the layered medium, as I showed earlier. So here from this figure, you can see this is the normalized nucleus size. And especially for the longer precursors, like in the order of days, we see that the nucleus size for this particular simulation can be reduced by like about 50% for different frictional parameters. So because of this reduction in the precursory velocity, like in the nucleation size, the precursory velocity drop can actually facilitate the slow sleep events that I showed earlier to grow into earthquakes. And here I want to show the relatively larger L simulations first because they are relatively simple. So if you look at the like the first time when the slow sleep events grow into earthquakes, you can see that after we have this precursory velocity drop, there is actually a really fast and abrupt linear growing of the sleep rate to the seismic values. And we can also look at the co-seismic sleep distribution for this no precursor case and one-day precursor case. And again, if you look at this initial rupture patch for the one-day precursor, it's reduced by more than 50% compared to the no precursor simulation. However, once these earthquakes are nucleated, we find that the magnitudes turn out to be pretty similar when the L is relatively large. So here we are showing the simulations for like 1 second, 5 hours, 1 day, and 20 days precursors based on different sleep rate threshold. So for this particular simulation, you can see the nucleation size here is generally reduced as we increase the precursory onsite duration. But the overall rupture extent or the average co-seismic sleep tend to be very similar to each other, except for this 1 second precursor scenario. But there could be more complexity in these kind of simulations, especially when we reduce the L in our simulations. So these two simulations are for a smaller characteristic weakening distance of 2 millimeters, just to demonstrate how variable the earthquake sizes could be. So here, if you look at, if you compare the no precursor to 20-day precursor simulations, you can see that generally when we have the precursors for L equal to 2 millimeters, we are actually seeing more earthquakes, but with less average co-seismic sleep. And also for some scenarios, we can see there could be slow sleep events in the no precursor simulation that are turned to the small earthquakes in the 20-day precursor simulation. And of course, we're seeing these smaller earthquakes can grow into larger ones in the 20-day precursor simulations as well. Well, just to conclude my talk here, I'm showing that when we have these near fault low velocity structures, the fault zone waves, they can generate the small scale stress heterogeneities. And in turn, we can have variable earthquake sizes and hypocenter locations. And these effects actually become even stronger when we allow these near fault materials to change over time. So for example, when we have this co-seismic damage and interseismic healing, we see that in the immature fault zones, we have slow sleep events that can propagate into the velocity weakening region and limit the earthquake sizes. But then when we have the mature fault zone scenarios, we actually have a very regular occurrence of surface rupturing events. So in the end, we want to investigate how the nucleation size is changed by the variation of the near fault materials. And we're seeing that only one, like a precursor value change of 0.5% can actually greatly reduce the nucleation size and accelerate the nucleation of the earthquakes. But whether these earthquakes will become larger actually depends on like the frictional conditions and the stress conditions on the fault more. So here I just want to show the classic earthquake cycle models again. And I think when people talk about these models, we're mostly talk about how the stress evolves over time. But I think we should also consider how the materials evolve over time. And that actually the evolution of the materials could be coupled with the evolution of the stresses as well. And because these material changes can be observed using seismic data or geodetic data, we should be able to understand this coupling between the material change and earthquake cycles much better. Thank you.